Imagine a universe where the tiniest flickers of energy hold the key to everything we see and experience. These fleeting disturbances, known as quantum fluctuations, are not just random events in the fabric of space and time. They are the seeds from which galaxies, stars, and even life itself may have emerged. But here's the twist. These invisible ripples could also unlock secrets far beyond our comprehension, like parallel universes or hidden dimensions. Quantum fluctuations happen when particles pop in and out of existence at unimaginably small scales, creating a cosmic dance that shapes reality on levels both minuscule and monumental. From the birth of black holes to the mysterious pull of dark matter, these tiny tremors ripple outward, influencing everything from the smallest atom to the vast expanse of the cosmos. And today, we're diving deep into 30 mind-bending theories about how quantum fluctuations might shape our understanding of the universe. By the end of this journey, you'll see why these ephemeral phenomena might hold answers to some of science's greatest mysteries, and maybe, just maybe, challenge everything you thought you knew about reality. Keep watching, because what comes next will take you to the edge of human knowledge and beyond. Let's start our journey with one of the most profound implications of quantum fluctuations: their role in the birth of galaxies. Picture this: the universe is just a fraction of a second old, an unimaginably hot and dense inferno where everything exists in a chaotic state. Amidst this chaos, tiny ripples in energy density emerge, flickering like fireflies in the cosmic night. These are quantum fluctuations, and as the universe rapidly expands during the Big Bang, they stretch across vast distances, becoming the blueprint for structure in the cosmos. Now here's how it works. As the universe cools and matter begins to form, these once tiny fluctuations grow into regions of slightly higher or lower density. In areas with higher density, gravity takes over, pulling in surrounding material and creating the seeds of what will eventually become galaxies. This process, known as gravitational collapse, transforms these minuscule disturbances into massive structures that span millions of light years. Modern simulations of the early universe beautifully illustrate this phenomenon. They show how quantum fluctuations, initially on microscopic scales, evolve into the intricate web of galaxies we observe today. These simulations reveal filaments of galaxies interconnected by vast voids, a cosmic tapestry woven from the smallest threads of quantum mechanics. It's truly mind-boggling to think that the majestic spiral arms of the Milky Way and the countless other galaxies in our observable universe owe their existence to these fleeting quantum events. So, next time you gaze up at the stars, remember that each galaxy you see started as a whisper in the fabric of space-time, a ripple born from the quantum dance of particles in the newborn universe. And this is only the beginning of our exploration. There's so much more to uncover about the profound impact of quantum fluctuations on the cosmos. Shifting our focus from the cosmic origins of galaxies, let's dive into one of the most mind-expanding implications of quantum fluctuations: their potential role in the multiverse theory. Imagine a universe where the fundamental laws of physics as we know them, gravity, electromagnetism, even the speed of light, are not universal constants but instead vary wildly depending on where you are in the cosmos. This is the essence of what some physicists propose could arise from quantum fluctuations during the early moments of our universe's formation. Here's how it works. During the rapid inflationary phase following the Big Bang, quantum fluctuations may have stretched across unimaginable distances, creating distinct regions of space-time with unique physical properties. In one region, gravity might be slightly stronger, while in another, the electromagnetic force could behave differently. These variations, if they exist, would essentially give rise to separate, bubble universes, each governed by its own set of rules. This concept gains traction when we consider brainworld models, which visualize our universe as just one of many brains floating within a higher dimensional space. Think of these brains like parallel sheets suspended in an invisible ocean, occasionally interacting through gravitational forces or collisions. Quantum fluctuations might act as the seeds for new brains to form, leading to entirely separate universes with differing characteristics. While this idea remains speculative, it opens up fascinating possibilities about the nature of reality itself. For instance, some theorists suggest that certain quantum fluctuations could result in universes where life as we know it couldn't exist due to incompatible physical conditions. Others propose that there might be regions where exotic forms of matter dominate, offering clues about dark energy and dark matter. Visualizing this concept can help make sense of its complexity. Diagrams often depict brainworld models as layered surfaces intersecting at various angles, symbolizing how different universes might coexist without directly interacting. By studying quantum fluctuations, scientists hope to uncover evidence supporting such theories, bringing us closer to understanding whether our universe is truly alone or part of something far greater. As we continue unraveling these mysteries, the implications stretch beyond science, touching philosophy and our very place in the grand tapestry of existence. But before we move forward, take a moment to ponder: could the smallest quantum events hold the key to unlocking the largest questions about our cosmos? Let's now turn our attention to another tantalizing mystery: the origins of dark matter and its connection to quantum fluctuations. While invisible to traditional observation methods, dark matter plays a crucial role in shaping the universe's structure, making up approximately 84% of all matter. But what if its presence, and even its behavior, could be traced back to those tiny quantum events occurring moments after the Big Bang? Mainstream theories suggest that quantum fluctuations during the early universe's inflationary period led to slight variations in energy density. As the universe expanded, these fluctuations condensed into regions of higher mass concentration, forming the seeds for galaxies, stars, and other cosmic structures. Interestingly, some researchers propose that dark matter particles might have emerged directly from such quantum processes. These particles, unlike ordinary matter, wouldn't interact with light, explaining why they remain hidden despite their overwhelming gravitational influence. But let's not stop there. Fringe concepts offer equally fascinating possibilities. One intriguing idea is that dark matter isn't just a single type of particle, but rather a spectrum of entities created through complex quantum interactions. Some speculative models even suggest that certain types of dark matter could arise from exotic phenomena like actions or sterile neutrinos, both of which may result from specific kinds of quantum fluctuations. Actions, for instance, are hypothesized ultralight particles that could emerge as solutions to the strong CP problem in quantum chromodynamics, while sterile neutrinos represent potential extensions of the Standard Model, possibly arising from vacuum fluctuations. Exploring these ideas reveals how quantum mechanics intertwines with astrophysics on an epic scale. By studying quantum fluctuations, scientists aim to bridge gaps between observed phenomena and theoretical predictions, offering new insights into dark matter's elusive nature. Whether through established frameworks or more unconventional approaches, the pursuit continues, driven by humanity's unyielding curiosity about the cosmos. So, as we delve deeper into this enigma, consider the profound implications. The tiniest quantum ripples at the dawn of time might hold answers to one of the universe's greatest unsolved puzzles. What do you think? Could dark matter truly trace its roots to these primordial fluctuations? Shifting our focus now to another mind-bending aspect of quantum fluctuations, let's explore the profound mystery surrounding vacuum energy density. This enigmatic phenomenon lies at the heart of one of the biggest challenges in modern physics: understanding why the universe behaves the way it does on a cosmic scale. In theory, empty space isn't truly empty, it's teeming with fleeting bursts of energy known as quantum fluctuations. These tiny ripples create what scientists call vacuum energy, an inherent property of spacetime itself. However, when physicists attempt to calculate the expected amount of vacuum energy based on quantum mechanics, they arrive at numbers that are astonishingly far from reality. In fact, the predicted value is about 10 to the power of 120 times larger than the observed energy density of the universe. This staggering discrepancy has been dubbed the worst prediction in the history of physics. So, how do quantum fluctuations fit into this puzzle? Well, these microscopic events contribute to the total vacuum energy by constantly forming and collapsing particles out of nothingness. Yet somehow, the net effect aligns almost perfectly with the incredibly small observed value, a balance so delicate that it defies easy explanation. Some researchers speculate that unknown mechanisms might cancel out much of the excess energy, while others propose radical ideas like anthropic reasoning. Perhaps we observe such fine-tuning because only universes with precisely this level of vacuum energy can support life. Regardless of the solution, the vacuum energy puzzle underscores just how much we still don't know about the interplay between quantum mechanics and cosmology. It invites us to reconsider fundamental assumptions about the nature of reality itself, reminding us once again that the tiniest phenomena can shape the largest scales imaginable. As research progresses, uncovering the secrets behind this cosmic conundrum may reveal entirely new principles governing the fabric of existence. What do you think could bridge this gap between theory and observation? Could the answers lie hidden within the intricate dance of quantum fluctuations? Building on the mysteries of vacuum energy, let's now turn our attention to another cornerstone of modern cosmology, cosmic inflation. This groundbreaking theory not only reshaped our understanding of the universe's early moments, but also highlighted the pivotal role played by quantum fluctuations in shaping the cosmos as we know it today. Back in 1979, physicist Alan Guth introduced the concept of inflation while trying to address several puzzling issues in the Big Bang model, such as why the universe appears so uniform across vast distances. His idea proposed that shortly after the Big Bang, the universe underwent an incredibly rapid expansion, a phase where space itself stretched faster than the speed of light. During this brief yet monumental period, tiny quantum fluctuations were magnified into large-scale structures, laying the foundation for galaxies, stars, and planets. Here's how it works. At the very beginning, the universe was a seething cauldron of quantum activity. These microscopic fluctuations, which would normally remain imperceptible, were stretched exponentially during inflation, becoming imprints on the fabric of spacetime. Over billions of years, these imprints evolved into the density variations we see today, regions slightly denser or less dense that eventually formed the seeds of cosmic structure. Recent observations from projects like the Cosmic Microwave Background experiments have provided compelling evidence supporting this theory. The subtle temperature differences detected in the CMB radiation align remarkably well with predictions made by inflationary models. These patterns essentially serve as a snapshot of those primordial quantum fluctuations, frozen in time just 380,000 years after the Big Bang. What makes this connection between quantum mechanics and cosmology so fascinating is its ability to bridge two seemingly unrelated realms. On one hand, you have the infinitesimally small world governed by quantum rules. On the other, the immense scale of galaxies and clusters spanning millions of light years. Through cosmic inflation, we witness firsthand how the tiniest ripples in the quantum foam can grow into the grand tapestry of the universe. As scientists continue refining their models and gathering more data, the story of cosmic inflation grows ever clearer. But there's still much to uncover. Each new discovery brings us closer to unraveling the intricate dance of forces that brought existence into being. How do you think future research might deepen our understanding of this extraordinary process? Shifting our focus now to one of the most mind-bending puzzles in theoretical physics, let's delve into the black hole information paradox and its connection to quantum fluctuations. This enigma lies at the heart of reconciling general relativity with quantum mechanics, two pillars of modern science that often seem at odds. First, consider what happens when matter falls into a black hole. According to classical theories, all information about the swallowed material is lost forever within the event horizon. However, things get interesting thanks to Stephen Hawking's groundbreaking discovery in 1974. He showed that black holes aren't entirely black. They emit radiation due to quantum effects near their edges. This phenomenon, now known as Hawking radiation, arises from pairs of virtual particles constantly appearing and disappearing in the vacuum around the black hole. Occasionally, one particle escapes while the other falls in, causing the black hole to slowly lose mass over time. Here's where quantum fluctuations play a crucial role. These tiny disturbances influence the behavior of the escaping particles, carrying away some encoded information about the black hole's contents. But this raises questions. Does this mean the information isn't truly lost, or do these fluctuations somehow scramble it beyond recognition? Theories 7, 8, and 9 attempt to address these issues by examining black hole entropy and the nature of information retention. Entropy, in this context, refers to the amount of disorder or hidden information contained within a black hole. Quantum fluctuations might increase this entropy during the formation and evaporation phases, effectively storing information in subtle ways we're still trying to understand. One perspective suggests that quantum fluctuations preserve a kind of holographic record of everything a black hole consumes, aligning with the holographic principle. Another proposes that the information may be released in scrambled form through complex entanglement networks created by the fluctuations. Yet another idea speculates that the paradox could dissolve entirely once we fully integrate quantum gravity into our understanding. As researchers continue exploring these possibilities, one thing remains certain: quantum fluctuations hold the key to unraveling the mysteries surrounding black holes. By studying them, we inch closer to bridging the gap between the largest scales of the cosmos and the smallest realms of subatomic particles. What new revelations await us in this quest? The answer lies hidden in the interplay of space, time, and the tiniest ripples in the quantum fabric. Let's now journey into the microscopic realm of spacetime itself, where John Wheeler's fascinating concept of quantum foam emerges from the intricate dance of quantum fluctuations at unimaginably tiny scales. At the Planck level, the smallest unit of measurement we can conceive, space and time are not smooth continuums as they appear to us on larger scales. Instead, they become a chaotic, ever-shifting froth known as quantum foam. Imagine this: if you were to zoom in far beyond what even the most powerful microscopes can achieve, past atoms and subatomic particles, you'd reach a point where spacetime itself starts behaving like a bubbling liquid. Here, quantum fluctuations create and annihilate virtual particles so rapidly that the fabric of reality looks more like a turbulent sea than an orderly expanse. These fluctuations warp spacetime into countless tiny loops and tunnels, forming structures akin to microscopic wormholes that flicker in and out of existence faster than the blink of an eye. This idea of quantum foam challenges our classical understanding of space and time, suggesting that at its core, the universe is far less stable and predictable than it seems. It also hints at deeper connections between general relativity and quantum mechanics, offering clues about how these two seemingly incompatible theories might one day merge. For instance, the presence of quantum foam could explain why certain phenomena, such as gravitational waves or black hole behavior, exhibit characteristics that defy straightforward explanation using traditional physics alone. To visualize this concept, think of spacetime as a calm lake viewed from afar. but up close, under intense scrutiny, that same surface reveals itself to be teeming with activity, tiny ripples, bubbles, and eddies constantly forming and collapsing. Just as water's apparent stillness masks its underlying turbulence, the universe's grand order hides a wild, unpredictable foundation shaped by quantum fluctuations. Understanding quantum foam isn't just theoretical curiosity. It has profound implications for cosmology and quantum gravity research. As scientists continue probing the mysteries of the Planck scale, the answers they uncover may reshape our comprehension of the very nature of reality. Could the secrets of the cosmos lie hidden within this frothy substrate of existence? The evidence suggests they very well might. Building on the chaotic nature of quantum foam, let's now explore how these tiny fluctuations might influence some of the most fundamental forces in the universe. Enter Eric Verland's groundbreaking theory of entropic forces, which reimagines gravity not as a fundamental force but as an emergent phenomenon arising from entropy and quantum effects. Verland suggests that what we perceive as gravity could stem from the way information is distributed across spacetime. In his model, quantum fluctuations play a crucial role in creating gradients of entropy, essentially differences in the amount of disorder or randomness within regions of space. These gradients generate a kind of pull that we interpret as gravitational attraction. Imagine spreading marbles evenly across a table. If you suddenly remove some marbles from one area, the remaining ones will naturally move to fill the gap. Similarly, areas with lower entropy tend to draw objects toward them, giving rise to the effect we call gravity. This idea aligns beautifully with our understanding of black holes, where immense concentrations of mass warp spacetime dramatically. According to Verland's framework, this warping isn't just caused by mass itself, but also by the distribution of information encoded on the event horizon, a boundary defined by quantum fluctuations. The more information packed into a given region, the stronger the gravitational pull becomes. Mathematically, Verland ties this concept to thermodynamics, using equations similar to those describing heat flow. For instance, he relates Newton's law of gravitation to the second law of thermodynamics, showing how changes in entropy drive gravitational interactions. While the math can get complex, the core idea remains simple. Gravity emerges naturally when you consider how energy and information interact at the quantum level. What makes Verland's proposal so fascinating is its potential to bridge general relativity and quantum mechanics. By framing gravity as an emergent property rather than a fundamental force, it offers fresh insights into long-standing puzzles like dark matter and dark energy. If correct, this theory could revolutionize our understanding of the cosmos, revealing a deeper unity between the smallest scales of quantum fluctuations and the grandest structures of the universe. Shifting our focus now to one of the most captivating speculative ideas in theoretical physics, let's delve into the concept of wormholes as potential outcomes of extreme quantum fluctuations. Wormholes, often referred to as shortcuts through spacetime, are hypothetical passages connecting distant points in the universe, or even different universes altogether. While they remain purely theoretical for now, some researchers suggest that these cosmic bridges might emerge from the chaotic dance of quantum fluctuations at the smallest scales. To understand this idea, imagine spacetime as a fabric riddled with microscopic bubbles created by constant quantum activity. Within this frothy environment, certain fluctuations could become so intense that they warp spacetime dramatically, forming tunnels or bridges between otherwise disconnected regions. These structures would be far smaller than an atom, but under specific conditions, they might expand to macroscopic sizes, large enough to potentially traverse. The mathematics behind this concept draws on Einstein's theory of general relativity combined with principles of quantum mechanics. According to these calculations, negative energy, a peculiar property arising from quantum effects, could stabilize wormholes against collapsing under their own gravity. This stabilization process hinges on exotic matter with unusual properties, which might naturally arise from extreme quantum fluctuations. While still highly speculative, this theory opens intriguing possibilities. If true, it suggests that the very fabric of spacetime is teeming with hidden pathways waiting to be discovered. Moreover, it raises profound questions about the nature of reality itself. Could we someday harness these quantum-born wormholes for interstellar travel? Or do they exist only as fleeting phenomena beyond human reach? Artistic renditions of wormholes help visualize these abstract concepts, depicting swirling vortices of light and warped dimensions. Such images not only inspire wonder but also underscore the importance of exploring how quantum fluctuations shape the cosmos in ways we're just beginning to comprehend. As research progresses, who knows what secrets these mysterious tunnels through spacetime may yet reveal. Moving from the speculative allure of wormholes, let's pivot to another fascinating realm where quantum fluctuations play a pivotal role: the concept of time reversal symmetry break. This idea delves into one of the most fundamental aspects of our universe, time, and explores why it flows in a single direction, a phenomenon often referred to as the arrow of time. At its core, time reversal symmetry suggests that physical laws should work the same whether time moves forward or backward. However, this symmetry is not perfectly upheld in reality. Quantum fluctuations may offer a key to understanding why. These tiny disturbances in the fabric of spacetime could subtly influence how particles interact, creating minute but measurable differences between processes that occur in one temporal direction versus the reverse. One example comes from particle physics experiments involving kaons and anti-kaons. In these studies, researchers have observed slight asymmetries in how matter and antimatter decay over time. While seemingly minor, such discrepancies hint at deeper mechanisms tied to quantum fluctuations. These fluctuations might nudge certain reactions slightly more in one temporal direction than the other, effectively breaking perfect time symmetry on a microscopic scale. To grasp this better, consider water freezing versus melting. When ice melts, entropy increases, aligning with the flow of time we perceive. But if time were reversed, would the process unfold identically? Quantum fluctuations suggest otherwise, proposing that they tip the scales ever so slightly toward increasing disorder, a hallmark of the universe's forward march through time. Experimental evidence continues to support this line of thinking. Observations from high-energy collisions in particle accelerators reveal subtle deviations from perfect symmetry, reinforcing the notion that quantum effects are at play. By studying these phenomena, scientists inch closer to unraveling the mysteries behind time's unidirectional flow. As research progresses, understanding how quantum fluctuations shape our perception of time holds profound implications, not just for theoretical physics, but also for comprehending the nature of existence itself. Could these tiny ripples in spacetime hold the secret to why time feels irreversible? The answer remains tantalizingly out of reach, yet every discovery brings us one step closer to solving this cosmic puzzle. Transitioning from the intricate dance of time and quantum fluctuations, let us now delve into a fascinating realm where laboratory experiments bring cosmic phenomena down to Earth. Theories 14 and 15 focus on Bose-Einstein condensates, a state of matter achieved at ultra-cold temperatures that allows scientists to study quantum effects on a macroscopic scale. These condensates mimic the conditions of the early universe and provide valuable insights into how quantum fluctuations operate in controlled environments. Bose-Einstein condensation occurs when atoms are cooled to near absolute zero, causing them to occupy the same quantum state and behave as a single entity. In this unique state, researchers can observe quantum mechanical properties that would otherwise remain hidden. By creating these condensates in labs, scientists have effectively replicated conditions similar to those during the inflationary epoch of the universe, allowing for direct observation of quantum fluctuations under precise control. One groundbreaking experiment involves generating density waves within Bose-Einstein condensates. These waves resemble primordial perturbations thought to seed large-scale structures in the cosmos. Through careful manipulation of magnetic fields and laser traps, researchers measure how these artificial fluctuations evolve over time, offering clues about their cosmic counterparts. Such studies not only validate theoretical predictions but also highlight potential applications in technology, such as improved precision instruments and quantum computing. Moreover, these experiments underscore the interconnectedness of microscopic and macroscopic worlds. What happens in the vast expanse of space may find its echo in the tiny confines of a lab bench. As we continue to refine our understanding of Bose-Einstein condensates, they promise to unlock secrets about both the origins of the universe and practical innovations here on Earth. This dual potential makes them an exciting frontier in modern physics research. Shifting our focus from the fascinating world of Bose-Einstein condensates, let us now explore an even more mind-bending concept: the holographic principle and its connection to quantum fluctuations. This theory suggests that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface at the boundary of space itself. While this idea may sound like science fiction, it has profound implications for how we understand reality, and quantum fluctuations play a crucial role in this framework. At its core, the holographic principle arises from black hole thermodynamics, where physicists discovered that the entropy of a black hole is proportional not to its volume but to the area of its event horizon. This revelation hinted at a deeper truth. Perhaps the universe operates much like a hologram, with three-dimensional experiences arising from fundamental data stored in two dimensions. Quantum fluctuations, those tiny ripples in the fabric of space-time, could represent the pixels or smallest units of information in this cosmic projection. When we consider quantum fluctuations through the lens of the holographic principle, they take on new significance. These fluctuations are no longer just random perturbations. Instead, they might encode essential details about the structure of space-time itself. Imagine every fluctuation as a brushstroke on an immense canvas, collectively painting the picture of our observable universe. This perspective challenges traditional notions of space and time, suggesting that what we perceive as continuous and tangible may emerge from underlying patterns of quantum information. Moreover, the holographic principle offers intriguing possibilities for reconciling general relativity with quantum mechanics, two pillars of modern physics that have long resisted unification. By viewing spacetime as emergent rather than fundamental, researchers can begin to bridge the gap between these seemingly incompatible theories. Quantum fluctuations serve as key players in this endeavor, acting as intermediaries between microscopic quantum phenomena and macroscopic gravitational effects. As scientists continue to probe the connections between quantum fluctuations and the holographic principle, their findings promise to reshape our understanding of reality itself. Whether or not the universe truly behaves like a hologram remains an open question, but one thing is certain: quantum fluctuations hold clues to some of the most profound mysteries of existence. With each discovery, we edge closer to deciphering the cosmic code that defines our place in the grand tapestry of the cosmos. Building on the intriguing possibilities raised by the holographic principle, let us now turn our attention to one of the most ambitious quests in modern physics: the pursuit of quantum gravity. This elusive framework seeks to harmonize the macroscopic world described by Einstein's general relativity with the microscopic realm governed by quantum mechanics. At the heart of this endeavor lies a profound question: how do quantum fluctuations influence and perhaps even define the nature of spacetime itself? Two leading approaches to quantum gravity stand out in this regard: loop quantum gravity and string theory. Both attempt to address the same fundamental challenge but take distinctly different paths. Loop quantum gravity focuses on reimagining space-time as a discrete lattice of interconnected loops, where quantum fluctuations manifest as tiny building blocks that collectively form the fabric of reality. In this model, these fluctuations are not mere disturbances. They are the very essence of space-time, giving rise to its properties at larger scales. String theory, on the other hand, proposes an entirely different picture. Here, particles are replaced by vibrating strings whose modes of oscillation determine their characteristics. Quantum fluctuations in this context play a critical role, influencing the vibrational states of these strings and shaping the forces and interactions within the universe. What makes string theory particularly fascinating is its potential to unify all fundamental forces under a single theoretical umbrella, though it requires the existence of extra dimensions beyond the familiar three of space and one of time. Both approaches highlight the crucial role of quantum fluctuations in bridging the gap between the quantum and gravitational realms. These fluctuations serve as mediators, encoding information about the structure of space-time while also affecting the behavior of matter and energy across cosmic scales. By integrating quantum fluctuations into general relativity, researchers hope to unlock answers to some of the biggest questions in science. What happened at the moment of the Big Bang? Why does spacetime behave differently near black holes? And how can we reconcile the smooth continuum of spacetime with the granular nature of quantum phenomena? While loop quantum gravity emphasizes discreteness and locality, string theory leans toward symmetry and multidimensionality. Together, they offer complementary perspectives that enrich our understanding of the cosmos. As experiments and simulations continue to push the boundaries of knowledge, quantum fluctuations remain central to unraveling the mysteries of quantum gravity, bringing us ever closer to a unified theory of everything. Shifting our focus to another captivating avenue in the realm of quantum fluctuations, let us explore the enigmatic world of action particles. These hypothetical entities have emerged as intriguing candidates for solving one of cosmology's most enduring mysteries, dark matter. Actions are theorized to arise from quantum fluctuations during the universe's earliest moments, making them a potential cornerstone in unraveling the invisible scaffolding that shapes galaxies and clusters across cosmic scales. At the heart of this investigation lies the strong CP problem in quantum chromodynamics, which prompted the initial proposal of actions. Quantum fluctuations in the early universe could have created vast numbers of these ultra-light particles, forming a diffuse cosmic web that interacts minimally with ordinary matter. This elusive nature makes actions an ideal candidate for dark matter, offering a solution that aligns with both theoretical predictions and observational data. Recent advancements in experimental physics have brought us closer to detecting these elusive particles. Cutting-edge facilities such as ADMCS and CAP utilize sophisticated resonant cavities to search for actions by converting them into detectable photons within strong magnetic fields. These experiments operate at incredibly low temperatures to amplify faint signals, pushing the boundaries of technology while narrowing down the possible mass range of actions. Meanwhile, astrophysical observations provide complementary evidence, with studies of neutron stars suggesting constraints on action interactions that further refine our understanding. What makes actions particularly fascinating is their dual role as both relics of quantum fluctuations and key players in dark matter dynamics. Their existence would not only resolve fundamental questions about particle physics, but also bridge the gap between quantum mechanics and large-scale structure formation. As research progresses, the interplay between theory and experiment continues to illuminate new possibilities, bringing us ever closer to confirming or refuting the presence of actions in our universe. This ongoing quest exemplifies how quantum fluctuations may hold the key to unlocking some of the cosmos's deepest secrets. With each new discovery, we edge closer to understanding the intricate tapestry of forces and particles that define our reality. underscoring the profound impact of quantum phenomena on the grand architecture of the cosmos. Transitioning from the enigmatic world of action particles, let us now delve into another fascinating realm where quantum fluctuations play a pivotal role: the generation of primordial gravitational waves. These ripples in space-time, born during the universe's infancy, offer a unique window into the cosmos's earliest moments and serve as crucial evidence for cosmic inflation. Quantum fluctuations in the early universe acted as seeds for not only large-scale structures but also gravitational waves themselves. As the universe underwent rapid expansion during inflation, these microscopic disturbances were stretched across vast distances, transforming into macroscopic distortions of spacetime. The resulting primordial gravitational waves carry an imprint of conditions just fractions of a second after the Big Bang, making them invaluable tools for cosmologists seeking to unravel the universe's origins. Detecting such ancient signals has been one of modern astronomy's greatest challenges. However, groundbreaking efforts by collaborations like LIGO and Virgo have ushered in a new era of gravitational wave astronomy. These facilities employ advanced interferometers capable of measuring minuscule changes in spacetime caused by passing gravitational waves. While most detections so far involve mergers of black holes or neutron stars, researchers are actively searching for the fainter signatures of primordial waves amidst the cosmic noise. The implications of detecting primordial gravitational waves extend beyond confirming inflationary theory. They could reveal critical details about fundamental physics at energy scales unattainable by terrestrial experiments. For instance, these waves might encode information about phase transitions in the early universe or even hint at exotic phenomena like cosmic strings. Furthermore, their study promises to deepen our understanding of quantum gravity, bridging the gap between general relativity and quantum mechanics. Efforts to observe primordial gravitational waves continue to evolve, with projects like the Cosmic Microwave Background Stage 4 experiment aiming to detect characteristic patterns in polarization known as B modes. Together, these endeavors highlight how quantum fluctuations, once mere theoretical constructs, hold the power to unlock some of the universe's most profound mysteries. Building on the profound implications of quantum fluctuations and their role in shaping the universe, let us now explore advanced cosmological models that incorporate these tiny disturbances into grand frameworks of cosmic evolution. These cutting-edge theories not only attempt to explain the observable universe but also predict phenomena yet to be discovered, showcasing the incredible power of modern cosmology. One such model is eternal inflation, which extends the standard inflationary framework by suggesting that inflation never truly ends. Instead, it continues indefinitely in some regions of the multiverse while ending in others, creating bubble universes with varying physical properties. Quantum fluctuations during this process determine the characteristics of each bubble, leading to a vast ensemble of possible realities. This idea challenges our conventional understanding of the cosmos, proposing that what we observe might just be one patch within an infinitely diverse landscape. Another intriguing approach is loop quantum cosmology, derived from loop quantum gravity. It addresses the singularity problem at the Big Bang by replacing the initial point-like singularity with a bounce caused by quantum effects. In this scenario, quantum fluctuations prevent densities from becoming infinite, offering a more complete description of the universe's earliest moments. Predictions from this model include distinct signatures in the cosmic microwave background radiation, potentially detectable through future observations. String gas cosmology represents another fascinating avenue, integrating string theory principles into early universe dynamics. Here, quantum fluctuations influence the behavior of strings vibrating across multiple dimensions, determining the eventual formation of familiar three-dimensional space. The model predicts specific patterns in large-scale structure distribution, providing testable hypotheses for astronomers. These advanced cosmological models demonstrate how quantum fluctuations serve as essential ingredients in constructing comprehensive pictures of the universe. By combining theoretical insights with empirical data, scientists continue refining these frameworks, pushing the boundaries of knowledge and revealing new layers of cosmic complexity. As technology advances, the predictive power of these theories will undoubtedly lead to groundbreaking discoveries, reshaping our understanding of existence itself. Shifting our focus now to another captivating aspect of quantum fluctuations, let us delve into the phenomenon of quantum tunneling and its surprising influence on cosmic structures. Quantum tunneling, a process where particles pass through barriers that classical physics would deem insurmountable, plays an unexpected yet crucial role in shaping the universe as we know it. This seemingly microscopic event has far-reaching implications, contributing to the formation of stars, planets, and even life itself. At first glance, quantum tunneling might appear insignificant compared to the grand scale of galaxies and stellar systems. However, when you consider the nuclear reactions powering stars, the importance becomes clear. In the cores of stars, hydrogen nuclei must overcome electrostatic repulsion to fuse into helium, releasing energy in the process. Classical physics suggests this fusion should rarely occur due to the high energy barrier involved. Yet, thanks to quantum tunneling, these nuclei can bypass the obstacle, enabling the continuous burning of stars over billions of years. Beyond stellar processes, quantum tunneling also influences planetary formation. Dust grains colliding in protoplanetary disks require specific conditions to stick together and grow into larger bodies. Quantum effects, including tunneling, enhance the likelihood of such interactions at tiny scales, facilitating the gradual buildup of celestial objects. Over time, these minute contributions accumulate, leading to the creation of entire worlds. Furthermore, this fascinating mechanism extends its reach into biological realms, affecting chemical reactions vital for life. Enzymes often rely on quantum tunneling to accelerate biochemical processes, ensuring the smooth functioning of living organisms. Thus, the same principles governing the cosmos also sustain life on Earth, bridging the gap between the vastness of space and the intricacies of biology. In summary, quantum tunneling driven by fluctuations shapes not only the smallest particles but also some of the largest structures in existence. By understanding these connections, we gain deeper insights into the interplay between quantum mechanics and cosmology, revealing the universe's intricate tapestry woven from both minuscule and monumental threads. As research progresses, uncovering further details about these processes will undoubtedly continue expanding our comprehension of nature's marvels. Experimental verification methods for quantum fluctuations provide a fascinating glimpse into the cutting-edge tools and techniques scientists employ to uncover the secrets of the universe. Transitioning from theoretical models to empirical evidence, researchers rely on an array of sophisticated instruments and missions designed to detect the subtle imprints left by these microscopic phenomena on cosmic scales. One of the primary ways scientists verify quantum fluctuations is through satellite missions dedicated to observing the cosmic microwave background radiation, or CMB. This ancient light, dating back to just 380,000 years after the Big Bang, carries signatures of the primordial quantum fluctuations that shaped the early universe. Satellites like the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck Observatory have provided detailed maps of temperature variations in the CMB, revealing patterns consistent with predictions made by quantum mechanics. These observations not only confirm the presence of quantum fluctuations, but also offer insights into their role in seeding large-scale structures such as galaxies and galaxy clusters. Ground-based telescopes also play a crucial role in this endeavor. Instruments like the Atacama Cosmology Telescope in Chile and the South Pole Telescope are specifically designed to study the polarization of the CMB. Polarization patterns, known as B-modes, can be attributed to gravitational waves generated by quantum fluctuations during the inflationary epoch of the universe. Detecting these elusive signals requires precision measurements and advanced data analysis techniques, pushing the boundaries of modern astronomy. In addition to studying the CMB, scientists use particle accelerators to simulate conditions similar to those in the early universe. By colliding particles at near light speeds, researchers recreate environments where quantum fluctuations might dominate, allowing them to observe phenomena such as vacuum decay and quantum tunneling under controlled settings. Experiments conducted at facilities like the Large Hadron Collider contribute significantly to our understanding of fundamental physics, bridging the gap between theory and observation. Furthermore, laboratory experiments involving Bose-Einstein condensates offer another avenue for investigating quantum fluctuations. By cooling atoms to temperatures close to absolute zero, scientists create conditions where quantum effects become macroscopically observable. These experiments mimic processes occurring in the cosmos, providing valuable insights into how quantum fluctuations influence matter and energy on both small and large scales. As technology advances, new missions and instruments continue to refine our ability to detect and analyze quantum fluctuations. Future projects, including next-generation space telescopes and interferometers, promise even greater precision and sensitivity, paving the way for groundbreaking discoveries about the nature of reality itself. Through these innovative approaches, science inches closer to unraveling the mysteries of the universe, one quantum fluctuation at a time. Shifting our focus from experimental methods to broader philosophical implications, let us now delve into theories 24 and 25, which explore the intriguing connection between quantum fluctuations and the anthropic principle. At its core, the anthropic principle suggests that the universe must have properties allowing for the development of life, simply because we exist as observers within it. When applied to quantum fluctuations, this raises fascinating questions about why certain types of fluctuations seem uniquely suited to creating conditions favorable for life. Imagine a cosmic lottery where countless possibilities arise from quantum fluctuations during the early moments of the universe's existence. Among these, only an incredibly specific set results in a universe capable of supporting complex structures like stars, planets, and eventually living organisms. What makes these particular fluctuations so special? Is it purely chance, or could there be deeper reasons driving this outcome? Proponents of the weak version of the anthropic principle argue that while the parameters of our universe appear fine-tuned, they are merely one realization among many possible outcomes. In other words, if the rules governing quantum fluctuations had led to a different configuration, no conscious beings would exist to question the situation. However, the strong form of the anthropic principle takes this idea further, proposing that the universe was somehow destined to produce intelligent life. This perspective opens the door to speculative notions such as multiple universes, each with varying physical constants, where ours happens to fall within the narrow range compatible with life. As we ponder these ideas, new questions emerge. Could quantum fluctuations themselves encode some inherent bias toward life-supporting configurations? Or is the perception of fine-tuning merely a reflection of our limited understanding of fundamental physics? These musings blur the line between science and philosophy, inviting us to consider not just what can be measured, but also why we observe what we do. By examining quantum fluctuations through the lens of the anthropic principle, we gain a fresh appreciation for the delicate balance that shapes the cosmos and perhaps even hints at our place within it. Transitioning from the philosophical implications of quantum fluctuations, let us now explore a more tangible phenomenon they may influence galactic magnetic fields. These invisible yet powerful forces play a crucial role in shaping the structure and dynamics of galaxies, affecting everything from star formation to cosmic ray propagation. But how do these vast magnetic fields originate? Recent studies suggest that quantum fluctuations during the early universe could be the key. In the moments following the Big Bang, tiny perturbations in the fabric of space-time created regions with slightly different densities. As the universe expanded, these fluctuations amplified, eventually leading to the formation of large-scale structures like galaxies. Alongside this process, researchers believe that quantum fluctuations also generated seed magnetic fields. These initial fields were incredibly weak, but over billions of years, processes such as turbulence and differential rotation within galaxies amplified them into the powerful forces we observe today. Observational evidence supports this theory. For instance, astronomers have detected magnetic fields in distant galaxies, some of which formed just a few billion years after the Big Bang. This suggests that the mechanisms responsible for generating these fields must have been active very early in cosmic history. Quantum fluctuations provide a plausible explanation for the origin of these primordial seeds, bridging the gap between fundamental physics and astrophysical observations. Moreover, computer simulations modeling the evolution of magnetic fields align remarkably well with real-world data. These models show how small-scale fluctuations can grow through dynamo effects, where motion within a conducting fluid, like the plasma found in galaxies, generates and sustains magnetic fields. By incorporating quantum mechanics into these simulations, scientists gain deeper insights into the intricate interplay between microscopic phenomena and macroscopic outcomes. Understanding the connection between quantum fluctuations and galactic magnetic fields not only sheds light on one of the universe's most mysterious forces, but also highlights the profound impact of seemingly insignificant events at the smallest scales. It reinforces the idea that even the tiniest disturbances in the early universe can ripple outward, shaping the cosmos as we know it. Building on our exploration of quantum fluctuations and their cosmic implications, let's now dive into one of the most fascinating frameworks that seeks to unify these phenomena: string theory. This revolutionary approach offers a unique perspective on how quantum fluctuations might behave across extra dimensions, reshaping our understanding of the universe's fundamental fabric. At its core, string theory proposes that the smallest building blocks of reality are not point-like particles, but rather tiny, vibrating strings. These strings exist in a multidimensional space, with some interpretations suggesting up to 10 spatial dimensions plus time. Quantum fluctuations, according to string theory, could represent ripples or disturbances within this higher dimensional framework. Imagine a vast cosmic tapestry where each thread corresponds to a dimension, and every vibration along those threads creates the particles and forces we observe in our three-dimensional reality. One intriguing aspect of string theory is how it explains quantum fluctuations as manifestations of energy variations across these additional dimensions. For instance, certain models suggest that the extra dimensions may be compactified, or curled up so tightly they remain invisible at everyday scales, but still influence observable physics through subtle effects like quantum fluctuations. In this context, what appears random or chaotic in our limited perception could actually follow precise patterns dictated by the geometry of these hidden dimensions. This perspective also addresses long-standing questions about why quantum fluctuations exhibit such diverse behaviors. By incorporating extra dimensions, string theory provides potential explanations for phenomena ranging from dark matter distribution to the fine-tuning of physical constants. Some researchers even speculate that quantum fluctuations in higher dimensions could generate entirely new types of particles or interactions, offering clues about unexplained mysteries like supersymmetry or the hierarchy problem. Moreover, string theory introduces the concept of brains' higher dimensional surfaces that can harbor entire universes. According to this idea, quantum fluctuations might cause collisions between parallel brains, potentially sparking events like the Big Bang itself. Such scenarios open doors to speculative yet captivating possibilities, linking quantum mechanics with cosmology in ways previously unimaginable. While still largely theoretical, string theory's interpretation of quantum fluctuations highlights the interconnectedness of all aspects of existence, from the smallest quanta to the largest structures in the cosmos. It invites us to rethink our assumptions about space, time, and reality itself, reminding us that the answers to life's greatest mysteries often lie just beyond the edge of what we currently understand. Shifting our focus now to another remarkable set of theories, let's explore how quantum fluctuations play a pivotal role in the creation of particles, a process that bridges the realms of quantum mechanics and astrophysics. Theories 28 and 29 delve into this fascinating intersection, offering profound insights into the origins of matter itself. At the heart of these ideas lies the concept of vacuum fluctuations. Contrary to what the term vacuum might suggest, the so-called empty space is far from being truly empty. Instead, it teems with energy, constantly giving rise to virtual particles that pop in and out of existence. These fleeting entities are not mere curiosities. They serve as the building blocks for more stable forms of matter under specific conditions. In Theory 28, we examine how vacuum fluctuations can lead to the spontaneous creation of particle-antiparticle pairs. When such pairs emerge near intense gravitational fields like those surrounding black holes, one member may fall into the singularity while the other escapes, becoming real matter. This phenomenon, famously described by Stephen Hawking, illustrates how quantum effects can transform abstract concepts into tangible cosmic processes. Moving on to Theory 29, we see how similar mechanisms operate on much larger scales. During periods of extreme energy density, such as the early universe's inflationary phase, vacuum fluctuations could have seeded the formation of fundamental particles. As the cosmos expanded and cooled, these primordial particles coalesced into the atoms and molecules we observe today. Both theories highlight the interplay between microscopic quantum events and macroscopic astrophysical phenomena, showcasing nature's intricate design. Together, these perspectives emphasize the deep connections between quantum mechanics and cosmology. By studying vacuum fluctuations and their implications, scientists continue to unravel the mysteries of particle creation, revealing the universe's hidden machinery in ever greater detail. Theory 30 expanded, future research directions as we wrap up our journey through the intricate world of quantum fluctuations. It's time to peer into the horizon of what lies ahead. The study of these enigmatic phenomena has already revealed astonishing insights, but many questions remain unanswered, beckoning scientists toward exciting new frontiers. Let's explore some promising avenues where future research could take us. One area ripe for exploration involves refining our understanding of how quantum fluctuations influence the earliest moments of the universe. While current models provide a solid foundation, advancements in observational technology, such as next-generation telescopes and space missions, are expected to uncover more precise data about the cosmic microwave background radiation. This will allow researchers to test predictions made by inflationary theory with unprecedented accuracy, shedding light on the role of quantum fluctuations during this critical epoch. Another tantalizing possibility lies in bridging the gap between quantum mechanics and general relativity. Efforts to develop a unified theory of quantum gravity continue to gain momentum, and quantum fluctuations hold a key piece of the puzzle. Investigating their behavior at Planck scales could reveal fundamental truths about spacetime itself. For instance, experiments involving Bose-Einstein condensates might simulate conditions akin to those at the smallest scales, offering clues about the nature of reality at its most basic level. Additionally, the potential applications of quantum fluctuations extend beyond theoretical physics. Emerging technologies like quantum computing and advanced materials science may harness these principles to revolutionize industries. Imagine computers capable of processing information using the very fabric of space-time, or materials designed to exploit vacuum energy for sustainable energy solutions. These possibilities, though speculative today, highlight the transformative impact that further research could have on everyday life. Moreover, the search for direct evidence of quantum fluctuations continues to inspire groundbreaking projects. Gravitational wave detectors such as LIGO and Virgo are paving the way for detecting primordial gravitational waves generated by quantum fluctuations in the early universe. Upcoming observatories, including space-based interferometers, promise even greater sensitivity, potentially opening windows into previously unobservable realms. In conclusion, the field of quantum fluctuations remains an ever-expanding frontier of discovery. With each breakthrough comes a deeper appreciation for the complexity and beauty of the cosmos. By continuing to push the boundaries of knowledge, scientists can unlock mysteries that redefine our understanding of existence itself. So let's keep exploring, questioning, and marveling at the wonders hidden within the quantum realm, and perhaps one day we'll fully grasp the secrets it holds. To wrap up our cosmic journey through the fascinating realm of quantum fluctuations, let us take a moment to reflect on the incredible theories we've explored and the profound implications they carry. From their role in seeding galaxy formation during the Big Bang to their potential connections with the multiverse, dark matter, and even black holes, quantum fluctuations have revealed themselves as pivotal players in shaping the universe as we know it. Each theory we've discussed adds another layer to our understanding of these enigmatic phenomena. We've seen how quantum fluctuations might influence everything from vacuum energy density and cosmic inflation to the intricate dance of entropy within black holes. They challenge us to rethink fundamental concepts like time, gravity, and the nature of reality itself. Whether it's the holographic principle, string theory, or the tantalizing prospect of wormholes, the possibilities seem almost limitless, and they remind us just how much there is still to discover. As we marvel at the beauty and complexity of the cosmos, remember that science thrives on curiosity and collaboration. If you found this deep dive into quantum fluctuations intriguing, why not join the conversation? Share your thoughts in the comments below. Perhaps you have questions about a specific theory or ideas for future research directions. And if you enjoyed this video, consider subscribing to stay updated on more explorations into the mysteries of the universe. Together, we can continue unraveling the secrets hidden within the quantum fabric of space-time. Thank you for joining me on this adventure, and let's keep the exploration alive.